Sweta, I think it's time to move to our last segment.
Yep, Saji. So our last session for APAC segment today is by Subhashish Ghosh. He is a cloud solution architect at Microsoft, and he enables the customers to build great solutions using the Azure platform. Hey, Subhashish. Subhashish is here to talk about how he enabled one of our Microsoft customers to migrate a graph solution from MariaDB and MongoDB for fraud analytics using the Azure Cosmos DB Gremlin API for faster performance, higher resilience, and better TCO. That sounds like a very interesting story of choosing the right database for the right use case to me, Subhashish. So over to you.
Yeah, hi Shweta, hi Saji. I hope I'm audible.
Yes.
Yeah, we can hear you.
Yeah, thank you for having me. Really appreciate. So I'll quickly jump into the use case, as you've already articulated, right? It so happens that I kind of worked with a lot of customers, and this specific use case. Again, though we are deep diving into this specific use case, where let's say the customer is kind of created, let's call it real time analytics on specific type of transactions which are coming through credit cards. But the learnings and the key design decisions that we will cover, I'll try to cover given our time's scope, definitely applies if you're also building real-time, let's say, recommendation engines, or for your e-commerce portal, or you're building social media analytics platform for let's say building a personalized marketing campaign and so on. So for this particular use case, right, initially the customer had built, let's call it a solution involving what we call traditional RDBMS, databases. So when you build a graph solution on top of that, we basically call it a RDBMS vertical graph solution. And they use a schema, basically, I've taken a kind of a representational image, is what we call a link table design approach. So what's the, some of the very important numbers related to the use case so that you have an idea of what kind of volume or veracity we are talking about. So first of all, this is all real time, and nodes or vertices, right? Talking about we had like around 2 billion, and around relationships between the vertices, which we call edges, right? Around 4 billion, give and take. So write volume TPS 40 million per day means it basically varied from, let's say, 500 per sec when non-peak, and to at highest peak, let's say 5,000 per sec. But that's the write volume, and the query volume it's a mixture of, let's say, mostly we try doing in partition queries and some point reads, but also upserts are there. So it's more of a write heavy, but with also some volume of query volumes as well, where you have some complex queries and a lot of point reads as well. So the point reads was around 250 to 300, let's say TPS per sec, and the number of graph queries per transaction used to vary between 40 to 50. So as you see, right, because it's a link table design approach, 10 years back when the customer kind of built the solution, in fact, I worked with very similar, a couple of other customers as well. They had all used a combination of different, databases which were available to them at that time. So for example, in this particular use case, the link, table, or let's call it the linkage data was stored in MariaDB. And the node, the edge detail data, it was initially stored in MongoDB. And what kind of traversals are you talking about? So more basic traversals were done again using relational join queries. So basically they were using a mix of primary plus foreign key relationships. And just for folks who are interested in total DB sizes, so we are talking about what, 6 billion database objects here, 2 plus 4. So the 2 billions were around, let's say, 0.5 KB. That's like 1 followed by 9 zeros. That's like 1 TB. And you're talking about the edges being 1 KB per edge object. That's around 4 or 5 TB. So give or take 4.5 or 5 TB of data you're talking about. Just if I move on to what was the query patterns which they were doing, and that's also one of the key reasons why more and more customers we see modernizing using Cosmos, is because it's relational, right? The top query patterns are all relational. So primary ops was a combination of insert update of the node edge rows. Like let's say for a customer, cust A, if I say, so I want to retrieve at a given instant of time, let's say all entities which are linked to the customer. So let's say, how many distinct, let's say, credit cards do you have? How many credit cards distinct cards did this particular customer use in the last 90 days? How many customers, let's say, shared a credit card with this person? So, you get some information about not just the discrete data points, but also, also ask all sort of questions about this customer vis-a-vis his or credit card. We will limit our conversation there because this was purely to understand the credit card discrete usage. But the key point to note here is it's not just from the customer to his email and so on, but also we want basically the solution required, let's call it architecture pattern, where we could do bi-directional traversal. That was becoming a bit difficult once you are on the relational RDBMS vertical graph solution. And we will take a look at some of the code, design patterns as well. We kind of chose. They became very key for scaling this, particular solution up. Now, if I talk about what kind of, so as I mentioned, the primary was the write operations in MariaDB, which included like insert, update of like node edge rows. But we also had considerable amount of, point reads as well. Now, what was the need for modernization? That's like a very important point to understand. Again, without like very basic generalization, because this varies from use case to use case. But in this particular use case, when we got involved with the team, there were fundamentally multiple, challenges. But if I take the top four, reasons for modernization, the first was handling the complexity of data growth. Now, I want to touch upon this, very important point, that when I say handling the complexity of the data growth, right, we are not meaning that storing, terabytes or petabytes of data, correct? The persistent layer was a challenge. No, that was not the reason. Specifically for use cases, if you're doing fraud detection, fraud analysis, recommendation engines, right? The common pain point that I have seen working with customers over the past 3-4 years, right, very actively, is as your data grows in a relational data store, and the deeper you basically want to kind of dive, storing data is never a core issue. The key challenge gradually becomes not just managing the discrete data points, but let's say a data point here is a record, which let's say in graph we call it a vertex, right? But it also very essential to these use cases is understanding and traversing the relationships between them, and between these distinct data points. So this easily fits into what we call discrete data and relational tables. So connected data and managing connected data becomes quite of a challenge. So for example, this customer specifically, when we did not 1x, but 2x, 3x traversals and more, again, not on 20 million, 40 million objects, but exceeding 100 million plus objects. When I say an object, I mean across an edge we are traversing, right? Given, let's say, a 1 KB or a 2 KB limit on our edge, we found that neither the performance, neither latency was good, and also it incurred cost in terms of doing complex querying using standard relational join queries. In other words, not just the traversing bit of it, but if you want to get millisecond level latencies in completing this traversals, it becomes very important to kind of look at optimized graph solutions and move from vertical graph solutions into something which can give you a horizontal scale. Number two, of course, this particular solution built over two RDBMS solutions lacked scalability, and traditional on-premises HA was though part of the solution, but the team needed to kind of scale the server during peak times. There was no SLAs per se in most of the customer use cases I worked. They wanted dedicated SLA on performance if it's available. Definitely on the last mile read latency, write latency, throughput would be excellent to kind of estimate and also optimize for. These two are very, very important points. And then, of course, because of the lack of the above mentioned points, there was a poor TCO for this particular use case. So basically, our recommendation was to use or check out Azure Cosmos DB, for let's call it Azure Cosmos DB Gremlin API. And since 80% of the query traversals basically were using let's say edges, so we basically wanted to kind of understand and also show the customer the value prop of the Gremlin API of Azure Cosmos DB. So let's quickly take a look at some of the key points so that it's clear. So I'll just show you a sample code of something which very much represents the customer use case, but this is not the exact customer code, just for a pointer. So this is in Visual Studio. We're using basically the Gremlin.NET, driver. And while we, kind of go through the code, we'll also talk about some key design decisions we kind of, specifically took a look at. So as you can see, for example, these are standard Gremlin, constructs. So when you're adding a vertex, right, you're basically mentioning a label because, for us, the Gremlin API, which is an Apache Tinkerpop standard, basically allows you to build what we call property labeled, graphs. You had an ID, which we, assigned to the vertexes, and then you had multiple properties. For example, for this particular use case, we stored the first name, last name, property, when there's this customer on board onto this e-commerce platform, let's assume. When did they use their last credit card? What credit card was it? What was his age? Now, this is a very, very, very important point. That's the partition key choice, possibly the most important design, decision for your, Cosmos DB, let's say, data model. Now, here I would like to touch upon one important thing. So if you see this, basically, right, this partition key choice. So it's basically a combination of my label and along with the ID. So we kind of tinkered with a couple of use cases. We tested out just using, let's call it unifier or identifier kind of a global, UID. We also created a partition key, a synthetic partition key with a concatenation of both, right? And we also wanted, we also tried checking out using a random, number generator. Now, one important point to note here is, can I replace this, synthetic partition key with a random number, or as a random suffix appended to my UID? You can, but again, the correct answer would be like, it depends, really varies from use case to use case. For example, I worked on a couple of use cases where it was extremely write heavy, but you did not, once you've written or updated a vertex, you never practically read it or, delete it or do any operations. You don't do much of a traversal. In such case, for very good or excellent write latency, it's good to have something which has very high cardinality. But for our given use case, we also had a post write, of course, an update of vertexes. We also had a considerable amount of point reads. So if you have a unique, let's say a random, prepended suffix or a prefix, right, it becomes very difficult to read a specific item. So that's basically the fundamental reason why we kind of chose a synthetic, partition key. Another important point was a design decision. And again, we tested these out, actually. That's the correct, way of testing it out. Another very important design requirement for this solution, when we were basically discussing, right, was to have, or the ability of where we have different kinds of relationships, but between the same vertexes. For example, in this, I have shown, for example, this particular, let's say, vertex, Subhashish, let's say, knows the second vertex called Abhijit. But it's also possible that, Subhashish knows him because he's working with him. Both are colleagues. So because that's also a fundamental reason when you're trying to study something like analytics, fraud analytics or social media analytics, you want to understand the different types of the relationships between these same vertexes. So that was also a very important design decision that was a bit difficult, when we tried remodeling this with the other, databases on offer. I mean, that's the input that we have received. Then very important was, let's say when we update the vertexes, we counted these are standard, Gremlin, operations. Another very important point is how do you limit or optimize for cost and latency? Is basically if you can, restrict or design your queries in such a way that they are in partition queries. So basically, you give the has with a partition key along with and restrict, so that that particular query is scoped to the logical partition where the data resides for that given partition key choice. Of course, we had traversals, so we tested out the basic traversals, the traversals for 1x, for 2x. For example, this one specifically is for folks that know customer 1, but also has, also knows customer 2. Then we basically had query patterns like this. For example, we wanted to understand all people older than a certain age and then more, create more complex, relationships between them. Then we basically wanted to understand that all persons were sorted. Then people who this particular customer knows, and people also known by those who this particular customer himself knows. So these were very important in trying to understand if there is a pattern between them in any of the usage of any blocked credit cards or any cards which had blocked APIs to it, or device specific IDs or device UIDs specific to that. One important also point which we leveraged, and we strongly recommend people leveraging, is always to use the execution profile. This is extremely important because it kind of gives you a lot of the parameters for which you can then deep dive into for optimizing queries, specifically from performance perspective, and then eventually moving into latency and then cost. And another very important point is for all of these queries, you have the status attributes. So the status attributes kind of prints out basically, the retry after milliseconds. That's basically, and also the unique identifier for the operation. So we used all of these, and we also used status attributes specifically for getting the what we call total server time and the total request charge. So if I kind of share the output on the screen, like let's say these are add vertexes, but let's say specifically I will go to an operation which is, let's say I'm doing a basic traversal, correct? I would like to know what's the status code. So we have a provide a list of status code, HTTP status codes, and very important for us is to check the total execution time and the request charge, which the RUs utilized for this query. So the recommendation is, and what we did was we tested out on the top 25 queries, and we wrote down specifically for the 1x, 2x, 3x till a certain n level depth, the query patterns, and we tested out also how we could kind of optimize using the execution profile, of course, and decrease the server time, execution time, and also the optimize for the request charge. Can I bring this 10.36 to, let's say, 8 or 5 or 6? This again is a very important design decision. Now, if I go to the portal, this is what exactly technically it looked like. I mean, of course, for 4 billion, edges, it will be much more complex in nature. And we also utilize a third-party, tool specifically for, visualization of this, let's say graphical representation. But as you see, the most important point, the fundamental reason why we wanted to test out or kind of enable this customer to migrate from a relational, join specific vertical graph to something which is horizontally partitioned, and let's say create complex relationships, was again on the basis of allowing them to store different type of edges and then traverse those edges to do operations on them. And then of course, as patterns emerge, you can feed them down to different downstream applications. And specifically, for example, if I go back to the presentation, I wanted to, so basically the troubleshooting aspect of it, definitely the recommendation is used to use the execution profile, which gives you an execution plan. And we use this very actively for optimizing, a majority of the queries. Another important point which I wanted to quickly highlight is the design decision choice, which is how do you effectively model for partitioning? I mean, this is a much larger discussion because partitioning, again, is a complex topic, but it's extremely well handled on your behalf by Azure Cosmos DB. So it handles it automatically. Only detail that you need to take care of, which, when you're in the pilot stage or, testing it out, is ensuring that you take care of the partition key, which allows you to kind of attain, scale. Another thing that we also optimized for was to keep in mind how do you design and optimize in-partition versus cross-partition queries. That is, there will be cases when you'll be traversing a graph which is connected across two partitions, because technically, though you may say that Cosmos DB provides you unlimited scale, but we have a logical partition limit of 20 GB, right? So it's basically, if you're talking about one object of 1K, so you're basically talking about 20 million graph objects, give and take. So estimating a total, data size again is something which is very important, which we effectively did. And that is very important because you can then check or test out your level of traversals effectively, where you can restrict. I mean, though in Cosmos, every outgoing edge is co-located with the vertex for you, but how do you optimize and kind of take care of this? Logical partition limit of 20 GB is something which is you should definitely take into consideration. Choosing a partition key I already covered, something which has high cardinality, but again, which can distribute throughput, storage, and operations for you. Give and take, again, a combination of both of these. And then another very important, consideration was cost measuring. Now, for this, we basically used a combination of both, client libraries, as I mentioned, but there are certain practices and patterns which you should be aware of. For example, g.v, that's not a very good query pattern because it's equivalent to a RDBMS table scan, right? Then again, g.v v1, like if you just give the identifier, like it basically fetches a vertex that has a specific ID. Not a very efficient thing because it's not possible to kind of uniquely identify a logical partition by the vertex ID only. So g.v1 dot has given that primary key. I mean, that is a good way of writing a query, right? So these also, again, are very important things which we took into consideration, right? And we tested out continuously the costs of the top 10, top 20 to 25 queries, including the top 4 levels of traversals. That's a good practice for cost measurement. And then, of course, optimizing it for latency, performance, and cost. Another also best practice which is recommended, which kind of we did, or it's basically to write down your query patterns for your given use case, and then try and estimate and come to an estimate sizing in terms of the total cost. Again, this is a very simplistic or rather oversimplification of our use case. But in real time, for example, as you see, I have given the vertexes, you have taken a sample code. I have tested out using code what's the number of RUs required for execution. Then you basically know for your use case the TPS. Then this is where in the real life you would like to kind of check out TPS for the on-peak versus off-peak periods, because you won't have 10 TPS, let's say, throughout the day, right? You will have times when you will have very low TPS, you will get peaks when it will be 10x or 5x of the TPS. And then you get to an average of adding both the two off-peak plus the on-peak, TPS, and come to a total RU, right? And we did this very effectively for many of the customer use cases I worked on, and it was very relative to what their sizing was eventually. Of course, give and take some of the operations which were over and not covered in these top 10 or top 20 queries. But once you have an idea of what kind of vertex you're adding, what's the length of the edge, what's the number of properties that you're gonna traverse, usually when you're traversing, then what's the level of updates you're doing. For example, are you just updating the vertex, or is it mostly very little creation of the vertex and the edges which you are mainly updating? Point read, something which is very efficient. Basically, you're bypassing the query operator, so you're directly going to the endpoint of the physical partition where the data is residing, right? So point reads you can definitely optimize for, but as we saw for our particular use case, let's say we had around 10,000 TPS, and when we scaled it up, let's say on peak is much higher as well. So your design decision of the partition key choice again has to be accordingly decided on that. Then the traversals, very, very key. We basically, for our use case, studied 1x in detail, 2x also in detail, till 3x, not beyond that. Because again, there has to be a very important point which needs to be mentioned here, though we are referring it as a media analytics or a social media engine you're building, or graph analytics, or let's say fraud analytics. But technically, you should leverage, let's say, building OLTP transactions using Azure Cosmos DB Gremlin API. And that's also one of the tips or design decisions, which is the last slide I have, which was some of the key learnings that we optimized for and picked up as we built the use case. That is, we wrote down the key query patterns. We effectively estimate data size. We chose the partition key effectively. We did did a couple of pilots. We estimated effectively and early, very important, and then eventually optimized for query latency and cost. And then if there were large volume OLAP workloads, then it's always good to offset that to Spark using the Spark connector, and then basically process it over there. So that's something which technically you should be aware of, and you should be kind of take away from here. So that's the crux of it, in terms of what we did, what we achieved. And of course, given the use case, the total amount of volume of the queries that we have is easily handled, is also the latencies are optimized for, and at 100 million plus objects for the pilots that we have done, and for some of the use cases that I worked in production as well. The optimization of the queries, if properly done with a choice of the partition key, can result in really highly performant systems for you, which of course you can then leverage other things with downstream applications and other integration of other services in Azure, right? And build a holistic solution. So vertical graph, if you have built or using a link table approach design, definitely do test out Azure Cosmos DB, and it will enable you to build really highly scalable graphs with low latencies and highly performant, and which you can with different tweaks in place, which you can really optimize for getting the best juice out of your solution, let's call it. So that kind of brings me to an end to this particular session.
Great. Thanks so much, Subhashish. This is, I would say, a great example of heterogeneous migration, right? And we know that the job is not fully done even after the migration is completed. So what are the tips and guidance that you've shared with the customer to make sure that this data model and setup is working well down the line? If it needs any optimization going further, maybe once their data size or their workload, or the number of requests grow, right? So what were your tips and guidance for that?
Yeah, estimating data size specifically is very key in building a graph solution, because it's not just about storing the vertexes, but one very important thing which we did was to before concatenating was to strip down the vertex sizes, because Cosmos for us is basically it's a property labeled graph, right? So properties play a vital role when you're doing the traversals. So to ensure that you have the most optimized data format is also very key. It's not just about storing. So in RDMS, for example, we see relational, often formats or records have a lot of data in it, which may not be required for a given use case. It's better then to kind of break the use case down into a graph solution versus a bit of it, which maybe the node detail, it's good to still be on a relational database, because the joins are much more simpler. You do not need sub-millisecond latency, and there's no practically, relationship traversal which is required. It's a pinpointed question, right? You can do it within an RDBMS solution or a key value pair. So that was a very important design, discussion. We had lots of it around it. So to ensure, so often we see that people or other, customers that we work with talk about, like, I have a 5 terabyte data. I would like to bring it to Cosmos DB and do a lot of operations on it. Though it's 100% possible, I would like to mention it, but that may not be the right approach for your given use case always. So to understand the data query patterns is more vital post, or rather, before you design the data model. So we did that very effectively. And also this was discussed that as your data grows, again, the discussion has multiple points. Is it just the data volume growth you're talking about? That is, I will add more vertexes, or will my use case change such that the properties and the number of properties will also grow? Because if I grow them as well and I traverse, my RUs do not remain constant. They will also vary over a period of time. So my total sizing will inflate both in volume, number of vertexes, properties, and also in the total sizing. So then, you have to revisit this data model after 6 months, strip it down, ensure that for your use case, it's highly optimized, then you will get sub-millisecond latency or very low level latency. So that's something which we, of course, it's open for discussion, and you have downstream applications which feed into this analytics. So you have to ensure also how do you upload that. And if you have an OLAP kind of a workload where the data sizes are large, again, recommendation is not to use Gremlin. Gremlin should be used only for OLTP. You should then possibly use a Spark connector to offload it to, Spark. So that is again a bit of the part of the solution which we are right now, let's say, working on.
Makes sense. Thanks for answering, Subhashish.
Yeah, I think one more question from my side I would ask, you covered one of the interesting scenarios on the fraud detection. In general, how can we provide a full text search functionality on graph data?
Okay, full text functionality. I am not aware of, but for us, it was like basically, I did come across this use case was to feed it into Azure Cognitive Services, and then use the indexing on the query parameters in Azure Cognitive Services, and basically use that indexer to search for the data. But then again, there are certain, I wouldn't call it caveats, but design decisions you need to kind of take into consideration. Like if your container source data changes, like how effectively would you re-index or rebuild the index on the Azure search? That basically is part of Azure Cognitive Search, right? We call it. So that definitely is something which we can take a look at.
All right. Yeah, thanks, Subhashish, for joining us. I think it was a great session that we had from you. So thanks once again.